All right. So basically, we've covered all rational numbers and decimals. So any fraction, which is a rational number, can be represented as a terminating or repeating decimal, which means the only decimals that we have left to think about are decimals that don't repeat and don't terminate. So they're going to be called irrational numbers. They cannot be written as a fraction. So an irrational number cannot be written as a fraction. So that's what I mean by an irrational number. So, what are some examples? Well, ones that are kind of common, the one that kind of everybody knows, is this number pi. And pi is like 3.141592653, whatever. So it just, I'll tell you the pattern, does not repeat. But you can imagine other ones. You could have something along the lines of, I don't know, let's do this one. Let's do 12.010010001000001, etc., keeping up that pattern. And you could say, well, there's a pattern there, so it must be able to be written as a fraction. But no, remember that in order to be written as a fraction, we showed that it needs to be a repeating pattern. So this is a this is a pattern, but it's non-repeating. So that's another example of an irrational number. And kind of the other ones that we'll talk about are square roots and cube roots, things like that. So another one is square root 2, and this will be shown later. So that's kind of one of the most common proofs in mathematics. Prove that you can't write square root 2 as a fraction. So the set of all rational and irrational numbers together, so all numbers, is called the set of real numbers. And it's denoted by a blackboard bold R. So an R that looks like that. So that's what I mean. So anytime we're talking about a number, we don't care if it's rational or irrational, we just want a number, then we call it a real number. If we want that it's a fraction, it could be represented as a fraction, we call it a rational number when we pick it out of the set of rational numbers, which we called Q. All right. So before we start, I need a couple of results. In fact, I'm just going to do it for the case of square roots, but I want to make a quick note that this can generalize to nth powers as well. But just in the interest of simplicity, we're just going to do square roots. So here's my result, is that a number is a square number, let's call it n, I guess. A number n is a square number. I'm going to use this biconditional notation. So if and only if all prime powers are even. And of course, even means divisible. Or let's say has a factor of 2. So, this if and only if, this is called a biconditional. So, it's kind of two if-then statements, two conditional statements in one. So we kind of have two parts here. So we have a P, the first part, and we have a Q, the second part. So what this if and only if says, so P, if, and only if Q, so that's logically equivalent. That's the same thing as saying if P, then Q, and if Q, then P. So it means it's exactly true. So just like what we were talking about with rational numbers and terminating or repeating decimals. A number can be represented as a terminating or repeating decimal if and only if it can be represented as a fraction. So it's the same kind of result. So this is what we need to show. So we need to do kind of two proofs here. So let's do the first one, if P, then Q. So assume that n is a square number. So that means that n must be m squared for some natural number m. And just to be clear, I just want to be clear that we are taking n in the natural numbers as well here. All right. So, what does that mean? We can come up with a prime factorization for m. So let's do it. So n equals, well, let's say m equals some prime factorization. Remember, every number has exactly one way you can write it as a product of primes. So just like in section in section 4.2, we're using that fact. So we're factorizing m into its prime factorization here. So this is the prime factorization for m. All right. So we've done that. Let's just put that in our formula. Thus, m squared is p1 to the e1 times p2 to the e2 times p3 to the e3 all the way to pk to the ek. And maybe I'm being a little careless here. Let me say that the p's are primes and the e's are indeed some natural numbers as well. They're the exponents for your prime factorization. Okay, so m squared equals that prime factorization of m squared, but we know our rules for exponents, so we have a whole bunch of things multiplied together to the exponent 2. So you just multiply each power by 2. So we have P1 to the 2 times E1 times P2 to the 2 times E2 all the way to pk to the 2 times ek. So, and remember, that's n. So we've shown that n can be written as a prime factorization where all the powers are even. Since all powers, or I should say all prime powers, of n are even, the result is proved. All right. But remember, this is an and statement. So we have the other if-then statement to do as well. So let's do it. Let's do the if Q, then P. And it's going to be basically the same work, just in the other direction. So assume that n can be written for, or what do I want to say, written as a product of primes with even powers. Okay, let's do it. So we should be able to write n as some product of primes. Let's use p's again. These are different p's. I just want to point out, it's kind of started a new part of this proof. So these p's stand for something else. So I'm kind of done with all these results up here. So I'm going to reuse some variable names. So these are, or maybe I'll, you know what? Just to make things a little clearer, they're different primes. Why don't I just use a different letter? So we'll use q's. So q is going to be our label for our primes. So we have q1 to the 2, I don't know, d1 times q2 to the 2, d2, all the way to ql to the 2, dl. So there's L primes multiplied together. Let's say for primes Q and exponents D. So we have L primes multiplied together with even powers. Here are the even powers. But I want to show that n is a square number, but that's pretty easy. I'm just going to refactor out that 2, just like I did. I'm going to do the reverse steps to what I did up here. That's what I want to say. So let's do it. So this is q1 to the d1 times q2 to the d2 times q3 to the d3 all the way to ql to the dl. And that's all squared. So I'm just using my rules for exponents in the other direction. So I have n equals something squared, this number here. Let's call that big Q. I already used Q for kind of the logical thing, so maybe I'll pick a different letter. How about A? So let's call all this A. So n equals A squared. So since A is a natural number, sure it is. Remember, the natural numbers are closed under multiplication, and this is just a bunch of natural numbers, a bunch of primes multiplied together. So that means that n is a square number. It's whatever A is squared. So the result is proved. All right. So we're done with our result for real now. We have both directions, which is great. Now we're going to use this fact to prove the following. So here's our nice theorem. If, hold on, let me pick, let's write it like this. If A, which is a natural number, is not a square number, then the square root of A is irrational. So that's what we're going to prove. So the square root of any non-square number is irrational. And our proof is going to be by contradiction. So we're going to pretend like there's a counterexample, and we're going to show that the world of math breaks. So we want to pick a number that is not a square number so that the p part is true, but it can be written as a fraction. It is a rational number, so the then part is false. So let's do it. So let A be a non-square number that can be written as a fraction. So, again, here's P true, and here is Q false. So we pretend like there's a counterexample to our if-then statement here. Here is P, so A is a non-square number, and here's Q. Square root A is irrational. If it's not irrational, then it's rational. And this whole bit is going to depend on the fact that we just proved that all square numbers have even powers of primes. Okay, let's go ahead and do it. Okay. So, since, what do I want to say? Since A is non-square, there must be one prime and its prime factorization that has an odd power. Let's call it P star. That's the one we're interested in. So let me just give you an example of what I mean. I'll just as an aside, I'll just use red. So this isn't kind of part of the argument, but it's just kind of getting at what we're doing with A. So suppose A is, I don't know, let's say 72. So 72 is 9 times 8, which is 2 cubed times 3 squared. Well, we know no number squared equals 72, and you can see that if you look at the prime factorization of 72. Here's our odd power. So the prime we're interested in is 2. Let's do one more example. What about, let's do, what if A was, let's do what? Let's do 160. No, let's do 80. If a is 80, well, 80 is, let's say, 8 times 10, which is 2 cubed times 2 times 5, which is 2 to the 4 times 5 to the 1. I'll just put a 1 here. You don't need it. But my point is, here's our odd power. So the p star, in the case of a equals 80, is 5. So that's the prime we're pulling out. There might be more than one. I mean, 6 is 2 times 3. They're both 2 to the 1, 3 to the 1. So you could pick either one of these guys. But there's always one. So we're just going to pick one of them. So that's kind of what we're doing, as long as you have that in your mind. All right. So we've picked our p star. So we know that a equals p star to the, let's say, the exponent e star times, let's say, a. A is just the rest. So it's everything else. We don't really care about it. The rest of the prime factorization. But we know that e star is odd. That's the key. All right. So we know how a looks in terms of its prime factorization. That's going to be key. All right. Now, we're saying that a is a non-square, and it can be represented by a fraction. So let's go ahead and do it. So, square root a. So square root a can be represented by a fraction. So let's say, suppose that square root a equals r over s for some r and s that are natural numbers. Okay. Excellent. So what we're going to do, it's kind of hard to deal with square roots. So to get rid of a square root, I'm going to square both sides. So a square root and a square cancel each other out. So we get that a is r squared times s squared, just r over s times r over s. That's what r over s squared means. And we'll multiply both sides by s squared, just to have no fraction. So we get that a times s squared equals r squared. All right, now the key. Let's count the number of p stars on each side. In fact, we're not really worried about the number of them. All we care about is if the number of them is even or odd. So remember, we don't know exactly how many p stars are in A, but we do know that there are an odd number of them multiplied together. So an odd number of p stars in A. Cool. Okay, so we know that. So let's look at the left-hand side. So since s squared is a square number, obviously it's s squared, s must have an even number of p stars in its prime factorization. And well, you could be thinking, well, how do we know there are any? But if there's none, then there's 0. But 0 is even as well. So that's fine. Okay. And since A has an odd number of p stars, well, let's figure out the whole number of p stars on the left-hand side. We have an odd number of p stars in A, an even number of p stars in S. And remember, when you have p star to the e star, remember e star is some odd number, times that they're the ones in A. And then we have p star to some, I don't know, I'll just write even, some even exponent. They're the ones in S squared. S squared has only even powers in the prime factorization. So that must mean, using our rules for exponents, we have an odd number plus an even number. We know an odd plus an even gives us an odd number of p stars. So we know on the left-hand side, we have an odd number of p stars. Now let's consider the right-hand side. Okay, so if we consider the right-hand side, what's going on? Well, r squared has an even number of p stars. Or you could think of it, the exponent of p star is even, right? Because that's what an exponent means. How many p stars do you have multiplied together? So the exponent is even. Now, think about that. So on the left-hand side, you have p star to some odd power. But on the right-hand side, you have p star to some even power. And these are supposed to be the same number. Remember, there was an equal sign between them. But there's no way they can equal if they have a different prime factorization. So the left-hand side and the right-hand side can't be equal, since they have a different prime factorization. Therefore, or thus, there's our contradiction. So we have a contradiction. We can't have it that the left-hand side equals the right-hand side and the left-hand side doesn't equal the right-hand side. So since we have a contradiction, we have two things that equal and don't equal at the same time, and mathematics breaks. Thus, there are no counterexamples. And the result is true. So that's great. So you can see here that take any number that you like, as long as it's a non-square. If you take the square root of it, you know for certain you can't write it as a fraction. So using this result, is square root, I don't know, 12 irrational? Well, let's check. 12 is 4 times 3, which is 2 squared times 3 to the power 1. So as soon as you see this odd exponent in the prime factorization, you know the square root of that number is irrational. So square root 12 is irrational. What about No, let's do 196. Is square root 196 irrational? Well, let's check. I don't know the prime factorization of 196 off the top of my head, so let's see what this looks like. So I can see a factor of 4 in there, since if you divide 4 into 96, you get a number with no remainder. So 196 is 4 times, and you can check, 49, and 4 is 2 times 2. 49 is 7 times 7, so 196 is 2 squared times 7 squared. But hey, look! I only have even powers here. Since they're all even, well, then I know that the square root of 196 is just, well, it's the square root of 2 squared times 7 squared. So it's just 2 times 7, which is 14. Great. So it is not. So the answer to this question, it's getting a little messy here, I apologize, is no. So hopefully that gives you an idea of what numbers, at least in square roots, can be written as as a whole number, and which can't. Basically, if the number is non-square, then it cannot be written as a fraction, as an irrational number. And I just want to make a quick note at the end here. So finally, we can generalize this to nth powers by changing all, let's say, squareds to nth powers, of course, even to has a factor of n, and odd to not a factor of n. And I'll leave that as a little exercise for anybody that's interested, but starting from that if and only if proof, everything goes through for nth powers. You just have to make those changes. It's a good little exercise if you're interested to see how this works in general.